Welcome everybody. Good evening. Vanakkam. So this is the first webinar for the PiCADS Motor software series. And in this webinar, we will introduce you to motors, what they are and how it works, how motors work, what are the kinds of motors, and also we'll cover the vehicle dynamics. Okay, I hope you're able to hear me. If not, you please put your question or concern in the chat window so that I know whether you're able to see the screen and also hear me right. Okay. So if you have any problem, just post your message in the chat window. So yeah, let me introduce myself. I am Srinivas Tangirala. I head the computer-aided design engineering tools at PiLabz. PiLabz has been established a couple of years ago. We are located in Govindapuri in Tenkasi district, and we are a manufacturing software CAD software development center through R&D. And let me also introduce my co-presenters. Supreet is a senior technical associate. He is well versed with the domain knowledge of motors and everything. And Oscar Anand, who will be presenting the motors, the first part, is a team lead for our software engineering team at PiLabz. So over to you, Oscar. You can start.
Yes, sir. Thank you. It's a very good start with a brief explanation of who we are. Uh, Hi, guys. Good evening. Uh, let's begin with our first slide. Okay. Let's start with most basic question. What is motor? Uh, I think you guys may have some idea, but from my side, I'll just give a basic line about what is motor. It's simply a device that converts electrical energy into mechanical energy. That takes electricity and turns it into a motion. Now, how does this happen? It's all about magnetism, a fundamental principle discovered by Michael Faraday. When current flows through a conductor inside a magnetic field, it experiences a force. In motor, there are two main parts, the stator and the rotor. Where the stator is stays still and the rotor rotates. The stator creates magnetic field and the rotor reacts to it. That's the basic outline of how motor works. And the second slide, uh, we'll move on to the uh, we'll just overview of parts of motor parts. What are the parts in motor?
Yeah. So basically, motors have been invented some 140 years ago. AC motor has been invented by Nikola Tesla, and DC motor some 200 years ago was invented by Michael Faraday. So continue, Oscar. Yeah.
Yes. Let me start from the right side, where you can see the cover, which covers the motor body, and then the rotor with bearings. Uh, why bearings? The bearings is used to give a mechanical support for the rotor to rotate smoothly with minimum friction. And the stator, which makes the rotors to rotate, which is inside the frame, you can see. And the other end is another cover, which covers from other side, and the cooling system. The motors will generate heat during the operation. So to control those heats, we will use the fans and the fins on the body through which the air flow. This reduces the heat. And other than that, this lifting eye and all for manufacturing stuffs like to lift the motor, they will use lift eye. And this nameplate, they will give the specs of the motor. And this in this wiring box, they will get the connection and supply the current. So we will go more deep about stator and rotor in further slides. Now, before we go deep into this technical part, let's first understand why we are studying motor fundamentals. You see, electric motors are part of every electric vehicles, like two-wheeler, three-wheeler, four-wheeler, and even buses. Now you can see EV buses in Chennai also, and not just EVs. They power Almost every modern machines you can think of, like washing machine, grinders, mixers, fans, pumps, and even spacecrafts. In industries, we talk about automation and mechatronics, right? All those robotic arms, conveyor systems, CNC machines, they all depends on precise motor control. Without motor, automation simply won't exist. Okay, now uh, let's, let us understand uh, motor parameters like torque, speed, current, and constants such as K and KT, which will be very useful in optimizing performance, improve efficiency, and design smart machines.
So this will be
Just
useful
to
for you
interrupt,
mechanical engineers as well as electronics engineers. We'll also cover a bit of the control systems for the motor. So basically, we'll be covering the design of motors, the parameters that control the motor efficiency and performance, as well as the control system. So for you, both mechanical engineers as well as electronics engineers, you will find this interesting. Okay. Yeah, carry on, Oscar.
sir, just to interrupt, you can also tell them about the poles.
Yeah, you speak.
Yeah. So, hi guys, this is Supreet. And as we go along the webinar, we will put up some polls just to gauge how much you already understand or how much you understand from this webinar. So, here's the first poll. So, you can all vote, and then we'll keep a tab of all those results. So, this is the first poll I'm starting. So, if you go to the if you go to your left panel, you can see, yeah, you can see the poll right now, and you guys can vote for it. So you can continue. You're voting for it, you can continue.
Yeah, next we will uh, learn about motor fundamentals and its physics. We know that what motor does. Let's understand how it actually works, the physics behind it. The whole operation is based on something called Lorentz force. In simple words, whenever current carrying conductors is placed inside a magnetic field, a force acts on it. This force is what makes the motor shaft rotate. Let me give an example, like, or you can think of it like this: an electric power you supply creates a magnetic field inside the stator, and this magnetic field interacts with the current in the rotor to create mechanical rotation. And we'll show the main core parts of motor, components of motor. Next slide. Now we understand how a motor works and physics behind it. Let's take a closer look at how it built, and the main components are stator, rotor, bearing, shaft, frame, and cooling system, which are listed here. The stator, which carries winding and produces the rotating magnetic field, as we discussed earlier slides. Rotor, which will be converts the electromagnetic force into torque. Bearing, which supports the rotor to rotate smoothly, and the shaft, which transmit mechanical power from the rotor to load. Like the stator makes the rotor to rotate, but how can we take the rotational motion from the rotor? So that we for that we are using this shaft, and the frame, which is used to protect all those parts. As I said, cooling system is the main thing, which removes heat generated in the winding and the core to maintain safe operation. Okay, then let us see what are the types of motors. Uh, in this flow chart, you can see a motor can be divided into AC and DC. In that AC, there is two separation, three phase and single phase. And in DC, there are brush and brushless. There are these much types of motors are there. But we will give us some most commonly used motors in industries and in our commercial life, so that you can connect with those motors. In next slide, we will just show what are the commonly used motor types. The first two motors are permanent, called as permanent magnet motors. These motors use magnets on or inside the rotor to help it spin. They are more efficient, smooth, and give high torque even at low speeds. I can give you some example in real-time example. Like think about an electric scooter like Ather or Bajaj Chetak. Use these motors for better acceleration and energy efficiency. And this SEAM is a squirrel cage induction motor. These do not use magnets. Instead, the rotor has a special gauge-like structure called squirrel gauge. They are robust, simple, and cheap, which makes very popular in everyday machines. I can give you like examples like ceiling fans, water pumps for agriculture, and AC compressor. These are the real-time examples for this SEAM. And currently, I came to know about that in trains also they are using Vande Bharat. They are using induction motors. And the last one is synchronous reluctance motor. These also same like SAM. They doesn't use magnets, but works by rotor following the magnetic fields of the stator. They are also very efficient, requires very less maintenance, and are slowly becoming popular in industries. For this, I can give example like industrial machines in factories, textile or engineering in Coimbatore or Chennai. They are using these motors.
Yeah, before we move on, I just want to explain the diagram. The blue one you see is the stator. The green one you see in the interior is the rotor. And between the rotor and stator, there is a very small gap. We call it the air gap. In that gap, which is about less than 1 mm, the magnetic field gets generated from the coils in the stator and the magnets in the rotor, or in the case of SAIM, the coils in the rotor. So that air gap is very, very crucial in the manufacturing of motor. So the precision has to be very good. And these are some of the configurations. In SPA surface permanent magnet, the magnets are curved along the surface of the rotor. And then internal permanent magnet, this is one of the configuration. The V configuration is one of the configuration of the magnets in the rotor. And you can also have a linear and many other configurations. So the configuration and design of those motors determines the performance and efficiency of the motors. In fact, I should mention that in Tesla, they use a combination of magnets and the synchronous reluctance motor design to get the maximum power. That is why Tesla cars are very popular. They are the most efficient motors manufactured so far. So, Oscar, you can continue. Yeah.
Yeah, yes, sir. As thank you, sir said, air gap is very much important. It should be between 0 to 1 mm. If the air gap is so high, the magnetic flux will not pass, rotor will not rotate. If it is more closer to the stator, it will crash the motor. So it should be very precise. Okay, then let us go on next slide of. This will be very useful because everyone should know what is back EMF. Back EMF stands for back electromotive force. Sim I can simply say like the voltage generated inside a motor when its rotor spins. When the current supplied to the motor, the rotor starts to spin. Uh, Inside, a magnetic flux field will be there. As it spins, the rotor behaves just like a generator and produces a voltage that opposes the supply voltage. That opposing voltage is called back EMF. Imagine a ceiling fan that is already running. If you try to spin it with your hand, you will feel a resistance. That resistance happens because the motor is generating voltage. This generated voltage is back EMF. When the motor spins fast, there will be a high back EMF. When it spins slow, low back EMF. And this is an graphical representation of back EMF. You can see the equation for this back EMF is, and it's like now you see what's the motor torque. Motor torque is the rotational force produced by the motor's rotor, which makes the shaft spin and drive the load. And it is the main reason a motor can rotate. Without torque, a motor would not be able to start or move any load. I will just give an example so that you can catch very easily. When an electric scooter starts moving, the motor produces the torque and turns the wheel. If there is a heavy rider or scooter is going in uphill, the motor needs to generate more torque to move smoothly. Motor torque decides how strong the motor is and how much load it can move or lift. That's the motor torque.
Yeah, in fact, the whole of motor design is designed to produce maximum torque. That is the efficiency. Depending on the efficiency, the torque is produced, and we'll talk about various types of torques: peak torque, rated torque. Oscar will continue. Yeah. So as you can see, it has the dimensions of Newton meter units. It is measured in Newton meter because force is measured in Newton, and the distance, the radius is from the center of the wheel to the surface, or tip of the wheel. So that is the radius of the rotor of the motor. So basically, radius is the distance from the axis of rotation, and F is applied tangential force. So that is produced by the rotating magnetic field. The rotating magnetic field is what makes the rotor rotate, and the way we measure the torque is the product of the radius and the force. So that's why it has the units of Newton meter. Okay, continue, Oscar.
Yes. And next, we'll see about KT, which is a torque constant. It tells how much torque a motor can produce for each ampere of current. When the torque constant is high, motor gives more torque for the same current. When the torque constant is low, motor needs more current to produce the same torque. In simple words, I can say like it shows how strong the motor is when current flows through it. When studying motors, several key parameters define how the motor performs. I have listed some of them. Let's understand one by one. KE, KT, as we already discussed, I will just give a one line of what is KE and KT and those things. How much voltage in the motor generated when it spins is the KT, KE, sorry. And KT is just how much torque the motor produces for each ampere of current. And the omega, this is an angular velocity, how fast the motor shaft rotates. And this is a number of turns. It's a number of wire turns in the coil. In stator, there will be a winding. They will use a copper wire. So this should be decided at the time. So number of wire turns in the coil for each slots. And then the number of phase. Motor can be defined into single phase or three phase. Three phase motors are smoother and more efficient comparatively. And the next thing is flux linkage. This shows how strongly the magnetic field links with the winding. Tmax is the safe heat limit of motor winding. If it is exceeded, motor insulation can get damaged.
Yeah. So why is the heat produced? Heat is produced because current is passing through the conductor, the coils. The coils are wound in the stator. There are certain slots, and meaning gaps in the stator, in which the coils are wound. The copper coil is wound. So the number of slots in the stator also determine the amount of or the magnitude of magnetic flux that is generated by the motor. So that is why you have number of turns of the coil and the linkage, and of course when the current passes through any coil, because of resistance the heat is produced. So we call it the I square R, because I square R is the power that the amount of heat that is generated is calculated by I square. The more the current you pass, more the heat is that is generated. So it is square times the resistance. So every copper wire, though it is a very good conductor, it has some resistance, and that resistance value multiplied by square of the current gives you the heat produced by current. There are also other factors that lead to the heat.
Yes, sir. And then now we will see the motor torque types. Motor can produce different types of torque depending on how long and how much load they handle. Let's go with the continuous torque. This is a steady torque that the motor can safely deliver continuously without overheating. Mm, It represents the motor normal working torque during regular operation. I can give you an example like when a scooter is in cruising smoothly at 40 km per hour, the motor provides continuous torque to maintain that speed. And for peak torque, uh, I can give it as example and then explain. When a scooter starts moving from a stop or goes in uphill, the motor gives quick extra push. This is its peak torque. The peak torque is this is maximum torque the motor can produce for a short period of time. That is peak torque. Stall torque. This is an same like peak torque where the maximum torque the motor can generate at zero speed when rotor is not yet rotating before the rotor starts rotating. But when a scooter tries to move from rest with a heavy rider, the motor produces maximum torque to start rotation. But if this condition continues too long, the motor can overheat or burn because no cooling occurs at zero speed of rotor. This is all about these torques. And next we will see about torque speed characteristics. Uh, uh, for every motor, the experts just see the torque speed curve, which is a relation between motor torque and its speed. It tells us how torque changes when motor speed changes. Like when the motor speed increases, the torque decreases linearly. At initial, we need high torque, but when speed increases, the torque will be reducing. But the power stays almost constant over most of the speed range.
Yeah.
And why it is important? Uh, while selecting a motor, engineers use this curve to select right motor for the job. Whether it needs more torque or more speed depends on their need.
Yeah.
And based on performance, it helps to understand how the motor will behave. For example, how fast it can accelerate or how much load it can pull.
Yeah. No, yeah, this torque speed curve also determines the behavior of the motor characteristic. So basically, the continuous mode, when the motor has to run in continuous mode, then you can determine what should be the ideal operating points. Operating point meaning what is the ideal speed. Speed, I mean the rotational speed in rotations per minute, RPM. That is the speed we are talking about, not the vehicle speed. So the torque is measured in Newton meter, right? So operating point is a combination of these two values. And the continuous operating mode, there will be one particular torque and speed values. So if we get this envelope, if we can calculate or determine this graph, we can safely determine what should be the peak operating points, what should be the continuous operating points of the motor. Okay. Yeah, continue.
Yeah. Now we will see the performance of motor. Losses under cooling, which is the main thing uh, for each and every motor. We should know about this. First, we'll see what are the losses, and then about the cooling system. First, I do you have any question? Why does motor get hot? Do you have any idea, guys? When current flows and magnetic field change inside the motor, some energy is lost as heat. These losses reduce the efficiency and must be removed to keep the motor safe and running smoothly. First, I will explain about copper losses. These copper losses are caused by current flowing through the copper winding. Uh, as we discussed, I square or the resistance of wire produces heat. When there is more current, it will generate more heat.
This is
So
from the
this,
basic Ohm's law. I think you all must be aware of Ohm's law, where power is equal to V is directly proportional to current. Voltage is directly proportional to current, and the constant is resistance. And power is V into I, voltage into current. Okay, so and voltage is IR, so that is why I square R. Okay, this is from Ohm's law. Yeah.
this copper loss limits how much current and the torque of the motor can handle continuously. For example, like a phone charger heating up and drawing more current. This is a simple example. And next thing is the steel loss, which occurs in stator and rotor lamination. There are two main causes. One is the eddy current losses, and other one is hysteresis losses. The eddy current losses uh, induce in a steel cause heat. Current induced in a steel cause heat, and hysteresis losses due to magnetic field changing direction many times per second. For example, um, friction inside a magnetic material. And the other final thing is cooling system. To keep the motor at a safe temperature, heat must be removed efficiently. Like most of the motors, they will use cooling fins and fans. The fans will be at the end of the back end of the motor, and the fins will be on the top, on the body, so that the air flow through the fins, and with air they will remove the heat.
Yeah, that is through convection. Convection is heat loss removal through air. So that is convection heat removal. And uh, through liquid cooling also we can remove some of the heat.
Yes, sir. For high power motors, they will use liquid cooling.
Yeah.
They will circulate the coolant over the motor. This system maintain the thermal balance and prevent overheating. In simple words, motor losses make heat. If not cooled, motor may fail. And this is a graphical representation of efficiency of motor throughout the operating points of torque speed curve. Where you can see the losses of mechanical losses, winding losses, copper losses, core losses. So with this, we need to calculate the efficiency, and this will show how efficient of our motors. Now,
The copper losses are maximum. 50% of the losses are accounted for by copper losses, which
copper
is
loss.
through the coil. Yeah. 30% for core losses, 15% for mechanical, and winding losses are about 5%. Yeah.
Okay. Now we have learned about some motor fundamentals like vacuum, torque, KT, and KE, torque speed curve. But now we will just go over a sample video of 10 minutes. This will help you how all these concepts actually happen inside the working motor.
So sorry, guys, the audio is not playing, I think. So you can just see this is explaining the concept of working of a motor through a circuit. Basically, there is a battery and a light bulb, and both are connected through wire. The bulb glows. And when you put a switch in between, you can turn the bulb on and off, right? This is a conventional flow of current. If you take the battery out and flip it, then also the light bulb glows because the direction of current doesn't matter. That is the circuit basics, right? Most of you know. Now you know every magnet has a south pole and a north pole. Okay, like this north pole also attracts paper clips, and the north-south like poles attract each other. Unlike poles attract each other, like poles repel each other, right? That is the basic principle of magnets. And every magnet has north and south pole. So this is what a permanent magnet looks like. And all it is comprises of little magnets which are aligned. And that's what it is showing. So if you make the magnet spin by putting a rod to the center hole, north repel each other, so it moves away, and south also moves away. So that's how the magnet keeps rotating if you keep on changing the second magnet's direction. Now we take a screw which has a coil wound around it. Now we get rid of the magnet, and this also, when you pass current, it behaves like a magnet, right? This got electromagnet. It also has north and south poles. Depending on the direction of the current, the poles change. If you pass it in one direction, the south pole becomes north, north pole becomes south. So the direction of the current matters in for the magnet, which side is the north and which side is the south. So an easier way to do this is to switch the wires also, right? Instead of changing the direction of the current by changing the battery, now positive and negative, you can even change the connections left and right. So he's showing one example of connecting the wires and changing. So that way, the south pole, instead of using a permanent magnet, we are now using an electromagnet and making that move through the hole in the which is supported by the rod. So same as earlier permanent magnet, this also keeps rotating if we keep switching the wires. If you put another permanent magnet there with the south and north on either side of the electromagnet, then it rotates even faster. Now let's say you even put a magnet around this. Instead of the electromagnet, we call this armature, which has like a rod, and you pass the current again. And you put this north and south pole magnet there. This also, now when you flip the current, it keeps rotating, right? Because the like poles repel each other. So the armature is called the commutator. That is what is a commutator, which will switch the direction of the flow of current, thereby making the armature closer to the magnet, same pole as the permanent magnet. As the commutator spins, the direction of current changes, and that's how it keeps rotating. This is called a commutator with brushes. So to pass the current in two different directions, we use the commutator, which is like a brush which is in contact with the commutator, which is like spinning. So that way the current direction keeps changing with every rotation. So this means that polarity keeps changing in the electromagnet, in the armature. Now it does everything on its own. So as long as you keep passing the current, the armature keeps rotating, right? So there is only one loop we have used so far. We can even split the commutator into two and have another armature. So this will increase the rotational speed. This illustrates the basic principle of rotation of motors through magnets and current. The magic of current and magnets. That's the whole point of this video. I hope you got the principle behind workings of the motor. So now you can increase further. I mean, you can increase several armatures, and the direction of the current in each of the armatures keep changing, and that produces torque. Stronger torque means stronger spin, and that's how the motor works. The more the number of wires or turns, the more the magnetic flux and greater the torque. So that's how the motor works. So in real motors, you have lots of windings, and you can get more torque. Depending on the application, you need to design the motor in a bigger motor or smaller motor accordingly. So that stator is what the windings will have. This is basically a DC motor. And even toothbrushes have a small motor inside of it. So you can design a small motor to a big motor, which even run trains and other even big vehicles as well. So the rotary motion can also be turned into linear motion. And of course, even fans can be rotated using the same motor. So this is all showing the applications of motor. Even the rotary motion of the motor can also be converted into linear motion. That is the cutting of the knives that can be achieved through this mechanism. Okay, so that's the video we just wanted to show. Hopefully you got the idea. Now we will shift to vehicle dynamics. Yeah, vehicle dynamics. Why are we doing this topic today? This is to understand from the specifications of an application of a motor, how do we design the motor based on the application? So that is what we're trying to do here. Taking the example of a vehicle, let's say a car. It doesn't matter what vehicle, whether it's a two-wheeler, three-wheeler, four-wheeler, or even a bus. Only thing that matters is the physics of it, which we'll go through. So any vehicle has these 5 driving modes, right? So what we will do is we will see how from the specifications of the vehicle, we will derive the specifications of the motor. So that is what we will do in this short session. So when you look at a vehicle, what is the purpose of a vehicle? It is, of course, it is used to move from point A to point B, but along the way, you have several drive modes of the vehicle, right? That vehicle, you'll be overtaking, meaning you will accelerate for some time, and sometimes you will just cruise at a peak speed. I mean, on a highway or something where there is no traffic, and then you can also cruise at rated speed, which is smooth cruising at a very comfortable speed. So there is a rated speed and there is a peak speed. Peak speed is maximum speed. You don't drive for a long time, but for a short peak time you will do it. And also sometimes you need to climb a hill, a short steep climb. So that is another mode. And a long uphill drive, this is another mode of driving where you need more power from the motor for the vehicle. Okay, these are the 5 driving modes of any vehicle, right? Because you will not be driving on a horizontal road or a flat road all the time. So if you look at each one of these driving modes, let's say the mode 1, cruising at rated speed, you have rolling resistance. The vehicle tires are in touch with the ground and it experiences resistance, right? And there is also air drag. I mean, you cannot avoid air wherever you drive. So maybe the air will be less dense at elevations than at the ground level, but you will experience air drag. And there is no climbing torque because you're cruising meaning you're driving on a flat road. So there is no climbing torque, right? And there is no acceleration torque as well. And the speed, of course, because you're cruising at a rated speed, the motor delivers that torque at that particular RPM. And that's how these are the characteristics of mode 1. Mode 2, please, next slide. In the cruising at peak speed meaning you are going at very fast speed. Let's say maybe 100 kilometers per hour, 80 kilometers per hour, whatever is the peak speed of the vehicle. Even the examples that Oscar mentioned, the Bajaj Chetak or Ola scooter, you have a peak speed, right? I mean, 80 kilometers per hour or 70 kilometers. If you're going at that speed, air drag will play a major factor as resistance because it has to overcome that resistance. So air drag will be considerable at peak speed, and rolling resistance will be the same. I mean, because only thing is the tires are rotating faster, but the resistance will be the same. And again, there is no climbing torque, there is no acceleration torque. And the speed is, of course, peak speed, meaning it is a very high speed, right? So speed is very high. So motor is rotating at a very high RPM. So mode 3, please. Oh, long uphill drive. If you're driving on a long uphill drive, well, the speed generally will be less. So air drag also will be less because more the speed, more the air drag. I will show you the physics behind it in the next slides. And rolling resistance will be the same. And climbing torque, because now you have to overcome the gravity, right? So you have to overcome the gravity. So you need a climbing torque to overcome the gravity. And you're not accelerating much. So probably the vehicle is going at a slow speed. So you don't have that acceleration torque. But maybe some speed you have to maintain to move up. Maybe not very high speed, but at least slow speed. So speed is also there. Okay. Now come to the 4th mode of driving, which is short, steep climb. The slope is very steep and you have to climb out of it. Okay. So the rolling resistance again will always be there because the vehicle is not moving at a much speed. So basically air drag will be almost be nil, not much, because the speed is very less. But climbing torque is very high because you need to overcome the gravitational force, and the acceleration also. You have to accelerate very much to come out of the steep climb, and the speed will be very less. I mean, it's not much. So these are the 4 modes, and the 5th mode is overtaking. In overtaking, your speed is kind of high, and so there is acceleration torque. You put it in 3rd gear or whatever and try to accelerate, right? So that's when you need more acceleration torque. And of course, there is no climbing torque, but there is air drag because it's not a slow speed. You have some speed which is considerable, and you will experience air drag, and rolling resistance also will be present. So these are the factors of 5 driving modes. Okay, we have seen. And now we will come to the physics of each of these driving mode. So basically, forces acting on a vehicle are from the Newton's second law, as you all must have studied in your school. Force is equal to mass into acceleration, mass times acceleration. And acceleration is rate of change of velocity, right? dv by dt. And m is the gross vehicle weight, and v is the vehicle velocity. So basically, for the vehicle to be moving, it has to have a traction force, which is represented by Ft, and it has to overcome the resistive forces, opposing forces. Fg is gradient force, and R is rolling friction force, and D is the air drag force. All these are opposing forces, these 3 forces. So whatever motor is generating the traction force will be somewhat nullified or opposed by these 3 opposing forces, Fg, Fr, and Fd. So you will have a net speed, net force acting on the vehicle, right? That is represented by F after overcoming the opposing forces. Okay, so this is very simple vehicle forces, like a free body diagram. We have analyzed this. Now we'll come to the other aspects. Next slide, Supri. Now, what is traction force? Traction force is basically the tau W to the wheel torque. Tau is represented, any torque is represented by tau, the Greek letter tau, and the subscript W represents the wheel. The wheel represents the wheel torque, and tau M is a motor torque. So traction force is the wheel torque, because wheel is the one which is driving the vehicle, right? Otherwise, whether it's a two-wheeler or three-wheeler, of course, four-wheeler has 4 wheels, two-wheeler are 2 wheels. So basically, for all the vehicles, the traction force will be represented by the wheel torque divided by the radius. So, and the wheel torque is equal to motor torque into G, which is the gear ratio, and into the gear efficiency. So basically, the electric motor will be somewhere inside the vehicle chassis somewhere, and that motor rotatory motion has to be translated to the wheels, right? So that uses a gear. I mean, depending on the gear ratio, how fast or how slow the vehicle has to go, it depends on the wheel torque will depend on the gear ratio and gear efficiency. So the main function of gear is to regulate the rotational speed of a power. The way is to give a ratio. Gear ratio tells you how many times the driving gear, the input, must turn to make the driven gear output turn once. So basically, you find gears everywhere. Even in watches, you have the gear, the second hand and the hour hand rotate differently, right? So that is how the gear mechanism is operates in the vehicle. So this is the traction force. This is a formula for calculating the traction force. Okay. So next slide, please. Now the gradient force. Let's analyze the forces acting on the vehicle when the vehicle is climbing on a slope. So basically there is gravity acting here, and if you acting vertically, so if you resolve the gravitational force along the plane and perpendicular to the plane, you have a gradient force mg sine theta, and the rolling resistance, which is acting opposite to the direction of motion of the vehicle, which is represented by rolling resistance, which is mu mg cos theta. The sine theta is perpendicular to the plane of the incline, and the rolling resistance will be the opposing the motion of the vehicle in the opposite direction. And of course, mu is the coefficient of friction. So this obviously varies whether you're driving on a muddy road or asphalt road, or depending on the type of road as well. So there will be some value of the coefficient of friction, but basically this is the formula for calculating the gradient force. Okay. Now next slide, please. So grade, when we talk about grade, 5 degrees, it is in degrees, right? So, but degrees is not practical. The way to represent is uh, in terms of the slope, I mean the rise. So let's say the vertical height is 87 meters and the horizontal distance is 1 kilometer. So we generally say it is 87 by 1000, grade is 8.7%. So if you take tan 5 degrees, then it will be 0.087. And in terms of percentage, it will be 8.7%. So 5 degrees is the average slope of hill roads in India. Even if we think we are driving on a flat road, on the average, I mean, generally in India, 5 degrees is supposed to be the average slope of hill roads in India, according to ARAI. ARAI is Automotive Research Institute in Pune. They are the ones who validate the vehicles. Any vehicle that comes into the market, they have to get certified. So they are the ones who do these tests, the gradient test and the acceleration test, all the tests they do for the vehicle, and then they certify the vehicle, then only it comes into the market. So theta will be, so what will be the angle if the steepest parts is 22% gradient? Then the angle will be tan inverse of 0.22, which will be 12.4 degrees. Okay. So that is how we calculate the grade. Next slide, Supreet. I hope we are doing the polls on this vehicle dynamics. So please test your knowledge as I'm speaking and your understanding. Okay, now let's come to the drag force. This is very interesting. Okay, so as you can see, the drag force is half rho, which is rho is the air density. As I said, the density varies according to altitude, right? The higher up you go, the rarer the air is and the lesser the density. On the sea level, of course, at the flat level, it will be much higher. And the CD is the coefficient of drag, which is again a constant, which is determined by several other factors. It's basically a number which will represent the force acting on the vehicle. And AF, of course, is the frontal area. The more the area that is gets exposed to the air, the more the air resistance, right? That's why you make the vehicles aerodynamic. All the shapes you see, the modern cars, they're very aerodynamic. They want the air to flow out very easily without much resistance, and also they help in reducing the air resistance. So that is also one factor, air frontal area, which gets exposed to the air as the vehicle is moving. And V square, this is very important. V is the velocity of the vehicle. You see it is V square. So if the vehicle is moving twice as fast, let's say from 20 kilometers per hour to 40 kilometers per hour, the air drag, multiplies 4 times, because 2 square is 4, right? So 2 times the velocity increases, air drag increases by 4 times. So pretty soon they will reach a limit. You cannot go after beyond a certain speed limit, because the air drag plays a very important role. And if you're going at very high speed, that's when your mileage or your efficiency reduces. So at very high speeds, like if you're driving at 80, 100, 120, even higher kilometers per hour, your efficiency, kilometers per liter reduces drastically, because it has to overcome, major part of the power is expended in overcoming the air resistance, right? So, okay, I hope you understood air drag. Next slide, Supreet. And putting it all together in this slide, we have now the bit of math. We'll just put together all these equations and do some math to arrive at what should be the motor characteristics. So these are the force equations for traction force, gradient force, rolling friction, resistance force, and drag force. So all these things put together, if you rearrange and get this A term, then you can arrange as an equation 3, as you can see, dv by dt plus A into v square is equal to B. So this is the final equation that you arrive at, which you need to solve to get the analytically, to get the specs of the motor. We'll see that in the next slide. Okay, next slide. So basically from this velocity, we arrive at, from this force, we arrive at the velocity versus time, and doing this integration, V is equal to, because it's a differential equation, to solve for V, you have to integrate, so, right? So if you integrate, you end up with this V is equal to root B by root A into 1 minus 2 by x e power 2 square root of ABT plus 1. So you do this math, and finally the steady state speed at V velocity at t infinite, because this is a velocity now depends on the time also. I mean, if the as the time goes, as time increases, this also changes. So at t is equal to infinite, V is equal to 0, t is equal to 0, then V's initial speed is also 0. At steady states where t is equal to infinity, V velocity will be root B by root A, which is like a terminal velocity. It cannot go beyond that speed, right? So this is how we determine the terminal velocity, I mean final velocity. So again, then now we got the velocity, right? Then you again integrate velocity, integral of V dt, you get the distance, because rate of change of distance is velocity. So ds by dt is V, so s is equal to integral of V dt. And then you plug in the equation for velocity, and then you solve this equation, you end up with distance is equal to 1 by A log e power 2 square root of ABT plus 1 minus root B by root A, all this log 2 by A. So this is the final equation for the distance. So now we got the distance, velocity, and as equations. Now with this, we'll be able to calculate the motor specs. I'll show you how. So velocity versus time at V is equal to 0 for a 6 Newton meter motor torque. You can see, like I said, the V t is equal to infinity, velocity is 37 kilometers per hour at 6 Newton meter torque. And for a vehicle with the 10 Newton meter, which is slightly higher torque, it can reach higher speeds. Maximum is 58 kilometers per hour. So that is how torque parameter plays in the performance of the vehicle. Yeah. So basically, the way these numbers are arrived at is there is an Excel sheet. I don't want to go into the details of the calculations, but basically arrive at the peak torque, peak speed, and all these characteristics of motor. And distance versus time for a 6 Newton meter motor torque, it goes up to maybe 1 kilometer distance, but for 10 Newton meter torque motor, you go a longer distance of 2 kilometers. Yeah, with the in the same time, 160 seconds. Yeah. So all these are calculated using Excel sheet, using the same formula that I showed you. So basically what we are saying is, if we define the vehicle, you take the vehicle parameters as gross vehicle weight 1000 kgs, gradient is 18%, gear ratio is 10, and wheel radius, rolling radius is 0.218 meters, frontal area is 3.7 square meters, and maximum gradient speed is 15 kilometers, cruising speed is 50 kilometers per hour, peak speed is 60 kilometers per hour. Here you have defined the vehicle. My two-wheeler or four-wheeler should have these specifications. From this, we can derive this motor. How? Like I said, the basic physics is what I had shown you earlier, but the details of this calculations is all embedded in our PiCADS a MotorCAD application, which you will get to see a few days from now. So we'll give you access to that. Then you will see defining the vehicle. You will get the motor specification. It does all these calculations behind the scenes, and it'll give you the rated torque, peak torque, rated speed in 1825, 1825 RPM. And like I said, like Oscar explained, rated torque is continuous torque, which for a longer period of time the motor can deliver, right? Peak torque, the motor delivers only 65 Newton meter, which is higher torque for a short period of time. If you try to, you know, uh, exert the motor or by passing more current or whatever to give more torque for a longer period of time, there are chances of the motor burning out, because of higher heat production and stuff. So that's when it gets damaged. So you don't want to do that. The recommended, as per the design of the motor, you're supposed to operate the vehicle as per the rated motor specifications. And rated speed is 1825, which this is the RPM of the motor at a continuous speed thing. And there is also peak speed, 7,300 RPM. Okay, this is one example of a motor. Okay, so don't take this for general thing. It can be any value. For different motors, the values will be different. So peaks, as you can see, this motor can withstand 7,300 revolutions per minute without breaking down. Obviously, the manufacturer has to ensure that it is able to withstand this speed, but even if this speed is reached, it should be only for a very short duration of time. Otherwise, there will be a risk of motor getting damaged. And then rated power, 10 kilowatt, and peak power is 15 kilowatt, and torque at peak speed nominal is 13 Newton meter. See, you see the difference between rated torque and nominal torque. Nominal torque is at 13 Newton meter and at 10 kilowatt, and peak torque is at peak speed is 20 Newton meter. So all these numbers, I think it will make sense for you when you get play with our software PiCADS motor. When you get a chance, you can log in and see, and you'll get a feel for these numbers. Okay. So I hope you enjoyed. So now, summarizing all that we learned today is motor specifications. We saw what the parts of a motor are, what is a motor, it converts electrical energy into magnetic energy, which gets converted to motion, rotary motion, or it can be linear motion as well. There are linear motors as well, but we are basically talking about rotary motion motors. And then we talked about these definitions. Peak torque is the maximum torque a motor can produce for short periods of time without exceeding the motor temperature limit. Thermal always plays a very important role in the design of motors. You don't want to design a motor which gets hot very quickly, then obviously it cannot be used, right? And if it gets hot, for example, when you're using grinder, the RPM is pretty high because it has to rotate at a very high speed to grind the ingredients which are there as a load, right? So when that happens, when you operate it for a longer period of time, motor gets hot. You're supposed to wait for some time, cool it down, switch it off, and then operate it again. So if you continuously do that, ignoring the heat, it will damage the motor. Yeah, it will burn out. So that's what you should be careful about. So you understood what is the difference between torque, the peak torque, rated torque, and peak power. Peak power output is the motor can deliver for a short period of time, as opposed to continuous or rated power without overheating. And peak speed is the highest rotational speed the motor can reach before the component failure, as I talked about. And continuous speed is the nominal speed at which the motor can continuously operate at the rated voltage and current to drive the full motor load. So the current that can be passed to the motor or the voltage depends on the number of motor pole, frequency of AC, and the amount of torque. Okay. So these are all specified by the manufacturer, but in our software, you can see how it is calculated. And no load speed, this is also a very important parameter. The maximum rotational speed that the motor shaft achieves when operating it is a rated terminal voltage without any external mechanical load. So basically, as you have seen the EMF that Oscar talked about, the back EMF is because motor also acts like a generator, in the sense it produces a voltage because magnetic field is rotating, and you have an electromotive force because of the motion of the motor. It acts like a generator as well at the same time, right? So that back EMF is almost equal to the supply voltage at this no load speed. So if you just take a motor and without passing current, if you rotate it using another motor maybe, so it will produce a voltage. At that maximum speed, that voltage that it produces is equivalent to the supply voltage without any load. And operating points, we talked about the torque speed curve, right? So that determines generally 70% or 60% of the peak torque and the peak speed would be the nominal operating point of the motor. Okay, for a continuous performance. But I mean, essentially, motor can run at many operating points, but it can run continuously and safely only at this rated operating point. Okay, which is the combination of torque and speed. Speed, I mean the rotational speed in RPM, revolutions per minute. Okay. Next slide, Supreet. So now that you learned about vehicle dynamics, and we also talked about this motor constants KT, KE, KT. KE is the back EMF constant relates speed to voltage, the rotary motion. So how do you control speed? You have to control the KE. And I don't know where we. So motors also have very important component called controllers. Controllers control the motor, meaning what? If you want the motor to run at a particular RPM and produce a particular torque, certain current only has to be passed to the motor. So that is controlled by the controller. So we'll talk about controller later. And this IRMS, the current that is supplied to the motor, even DC motors, they convert to AC through this controller, and the AC current is what makes the rotational magnetic field, which makes the rotor rotate. So that is the basic things about motor. And current DC max, maximum continuous current, is the current DC max. And RMS is root mean square current. Root mean square means because the current actually is flows in AC in a sinusoidal wave pattern, right? It has both positive and negative components, goes up and down. So if you average it out, everything turns out to be zero. So how do you determine the magnitude of such a current in AC? You take the root mean square. I mean the square root of the root of the square of the current, that is called IRMS, and which is drawn under rated conditions. That is the IRMS. So in PiCADS, we calculate this current, and then there is also some more details on how do you get the IDIQ, how do you calculate the torque current, how do you calculate the KT, KE, all these are calculated. That is why we are mentioning or exposing you to these terms, so that when you use the software, you will understand what they mean. Okay. Well, this is the first level understanding. You'll get more familiar with it when you start reading the document or help files, support files in the application. Yeah. Now there's a question for you. You're going from school to home. So in a vehicle, let's say a two-wheeler like a Bajaj Chetak or Ola electric vehicle, and you can drive fast, you will draw more power for less time, right? Or you can drive slowly, but you will draw less power for more time. So energy is equal to power times the time. So which drive will drain your battery more? This is a question you can answer. So and you have to reach in time. So if you accelerate, and so obviously you have to maintain the your vehicle speed constant, which is actually a challenge because you'll encounter speed breakers, some maybe some other obstacles. So your speed also varies. But as much as possible, if you maintain the constant speed, you will not drain your battery more, because if you accelerate, it draws more power from the battery and the battery will drain faster, right? So you have to draw less current so that you can reach in time, and also it'll draw less power from the battery. So that is what you think about it. How do you, which drive mode you should do to maximize the range of your vehicle or draw less power from the battery? And there is some other calculation on the left: energy consumption, what watt hour per kilometer, how is it calculated? Power in watts and V in velocity. Power is rotational speed of the motor into the torque of the motor. And torque of the motor is also given by, like we talked about, the gear ratio uh, into the V by R, which is the motor gear ratio. So that's how we calculate the watt hour per kilometer, and that will give you the specs of the electric vehicle. Okay, so I hope you have learned something today, interesting, and we will share these references with you. There is also books on mechanical design of motors and all that. So one thing you should understand is it's a multidisciplinary domain. Like it's mechanical engineering concepts coupled with thermal, coupled with electromagnetics. So it's also for electronics engineers and stuff. So it's a complicated subject that people have been studying and mastering for over 200 years now, more than 150 years. And the latest and greatest techniques that have been used are resulting in this electric vehicles nowadays. And so hopefully what you learned today will be of use to you in your career going forward. I think with that, I would like to end this webinar. So thank you all for attending this first webinar. Appreciate your time. And if you have any questions, feel free to email us at picads.course@pilabz.in. We'll be happy to answer your question and be in touch. Okay. And Oscar also has shared the video link in the chat. You can copy it and play it some other time. In your free time, you can watch it just to understand how motors work. I hope you all have found this interesting, and look forward to seeing you in the second webinar on 28th. Okay, we'll send out the webinar link again one day ahead of the webinar, and that will be on finite element methods. Like how do you know, how do you design and test, or estimate the efficiency and without actually making the motor? The way to do that is to simulate the motor behavior and performance. And there's a technique called finite element methods that we will introduce to you on 28th. Okay. With that, I will end the session. And if you have any questions, you can post it on the questions chat window.
Polls, they seem to have done very well, sir. Except
Good.
for a couple of questions, they mostly have given right answers. I think we can log off.
All right, we'll close the session. Yeah. Thank you.